Good morning, students. We'll start with today's lecture. Yesterday, we have seen the derivation for expression for the peak overshoot MP, right? This we have seen. And there is no derivation for TS and steady state error. We have seen the derivation for peak overshoot MP. And we were solving few numericals. We'll continue with this. And today we'll also see after a few numericals. Once again, we'll start with the steady state errors and error constants, right? We'll continue. Okay, we'll take up this numerical. Okay, the system shown in the figure 4.18a when subjected to a unit step input gives the output response shown in the figure 1.8b. Determine the values of k and t from the response curve. We have to find out the value of k and t, right? Okay, what is the value of k and what is the value of t, right? So this is g of s, the forward path transfer function, and h of s, the feedback path transfer function. It is 1 here. H of s is 1, right? Okay, and this is the system, given system, and this is the response of the system. You can observe here, this is damped sinusoidal damped oscillations, right? Damped oscillator in nature. And you can observe here, from here to here, this is MP, right? Whatever they have given is MP. Peak overshoot MP, it is 0.254, right? From here to here, it is the peak overshoot 0.254. And this time, you can observe here, this is the peak time, TP. Right, this is TP. What is TP? TP is equal to, let me write here, TP is equal to 3 seconds, right? This is 3 seconds. 3 seconds. Now from the response curve, we came to know that the peak overshoot MP is 0.254 and the peak time is 3 seconds, right? Okay, we'll make use of this data in order to get the value of K and T. Okay, first we'll obtain the transfer function C of S by R of S, right? Okay, this is, okay, we'll try to obtain the transfer function C of S by R of S. C of S by R of S is G divided by 1 plus G of S into H of S, right? Here G is this is G and this is H. H of S is 1 here, right? Okay, S into 1 plus ST. This is G divided by 1 plus GH. This is G, S into 1 plus ST. Okay, we will solve, we will take LCM. S into S plus T will get cancelled. So just we will multiply S square, S into S square T plus S into 1, S plus K. So this is the transfer function what we are getting. Compare this denominator with the standard second order system equation, that is S square plus 2z omega ns plus omega n square. You take the denominator equal to 0, right? So only compare the denominator. So while comparing, we came to know that omega n square is equal to k. So omega n square is equal to k, and 2z omega n. 2z omega n is equal to what? Let me find it out. So 2z omega n is nothing but 1 here, right? 2z omega n is 2z omega n is 1. Okay, I have made a mistake here. I should not compare directly because you can observe here it should be in the form s square plus 2z omega n plus omega. So just let me scratch it and rewrite it. So let me take t outside, t. So this t is taken outside, means k by t it will become, divided by t is taken outside, right? So what I am getting, s square plus t is taken outside, right? So s by t plus k by t. So call this as equation 1. Now this is of the form s square plus 2z omega ns plus omega n square. Okay, omega n square is k by t, sorry, right? We will compare this. Omega n square is k by t. Please don't make such mistakes what I have made now right now. 2z omega n is 1 by t. 1 by t. Right? Okay, fine. Call this as equation 2 and we'll later on we'll see proceed. Right? We'll make use of other equations and call this as equation 2. Omega n square and both. Then we will make use of the given data. MP is, peak overshoot is 0.254. MP is equal to 0.254. And TP is how much? 3 seconds. Let me write it here. 3 seconds. Okay. We know the formula for MP, e to the power of minus pi into z divided by root of 1 minus z square, that is equal to 0.254. So from this we can find out the value of z. So take ln on both sides, not natural logarithm, ln. Take ln on both sides, right? So it is not log, it is natural logarithm ln. So take ln on both sides. So if I after taking ln on both sides, pi into z divided by root of 1 minus z square. So ln of 0.254. Take, let me write it here. Take ln on both sides, both sides. So ln of okay, I am using the calci, ln of 0.254, 0.254. So how much I am getting? So it is minus 1.3704. Okay, then okay, I want value of z, right? I can calculate it. So this is any minus minus, they will get cancelled. This pi will be taken this side. So z divided by root of 1 minus z square, right? Okay, so minus both sides, right? So this pi divided by pi, 1.3704, 1.3704 divided by this pi, divided by pi. So I am getting it as 0.4362. So squaring on both sides, I want to find out the value of z, right? Square on both sides. So z square divided by 1 minus z square. So whole square, right? Z square, right? This root will get cancelled. It is equal to 0.4362 whole square. Square on both sides. Square on both sides. So 0.4362 whole square. 0.4362 whole square. I am getting it as 0.190, 0.1902. 0.19. Let me restrict here only. Right? Okay. I want to find out value of this. So I will continue further. Before that, let me check it whether I will get something here. Tp is equal to pi by omega d. We know this. And what is omega d? Pi by omega n. Omega d is nothing but omega n into under root of 1 minus z square. That is equal to 3. Right? So from this we can calculate z. Later on we will substitute z and we can calculate omega n. Right? First we will proceed with this. So z square into, just will multiply 0.19 minus 0.19 z square. Is it fine? Okay. Let me proceed here only. From here I am proceeding here. Is it fine? Okay. 1 minus 1 plus, take this side. Is it fine? So I multiplied, right? So take this side. So 1 plus 0.19. So 1.19 z square. Right? Take this side. 1.19 z square equal to 0.19. Is it correct? Okay. Next, z square equal to 0.19 divided by 1.19. So 0.19 divided by 1.19, I am getting it as 0.159666. So z is equal to root of this. Z equal to root of 0.15966. So I am getting it as 0.399, right? Okay, here just I am telling my answer. It is correct. 0.399 is 0.4 they are taken. 0.399. So let me round it. 3995. So I'll round it to 0.4. No problem, right? 0.39 is nothing but 0.4 I can make it. So the value of z is 0.4. So substitute the value of z here and find out omega n here, right? So from this, next, so I'll go to the next slide. Tp equal to pi by omega d is nothing but omega n into under root of 1 minus z square, and that is equal to 3 seconds. And we have found out that z equal to 0.4, right? So let me check it. Z is 0.4. So substitute here. So pi divided by omega n into under root of 1 minus 0.4 whole square equal to 3. Okay. Next we'll find out, we'll take this omega in this side and 3 this side, right? So omega n is equal to, take this omega in this side and 3 will come here. Pi by, right? Pi by 3 into root of 1 minus 0.4 whole square. So you calculate this, you will get omega n. So we'll calculate this. So I will calculate denominator first. 3 into root of open bracket 1 minus 0.4 square close the bracket. So I am getting 2.74. Take inverse of it so that it will go to numerator. Then multiply with pi. Multiply with pi. So I am getting 1.142 radians per second. So we have found out z and omega n. But what actually it is asked, value of k and t we have to find out, right? So here you can observe from equation 2, omega n square is k by t. Omega n square is what? Omega n square is k by t, and 2z omega n is 1 by t. 2z omega n is 1 by t. So here we want to find out k and t. Here we know the value of z and omega n. We can find out t here. Is it fine? So we'll proceed with this. So t is equal to 1 by 2z omega n. Right? Take t this side and 2z omega n this side. So calculate this. Value of z is 0.4. Substitute here 1 by 2 into z is 0.4. Omega n is 1.142. We calculate this. We'll get it. Right? 2 into 0.4 into 1.142. So take inverse of it. 2 into 0.4 into 1. Take inverse of it so that I will get t is equal to 1.094. So this is the value of t. So making use of this, we can find out k here. K is equal to what? Omega n square into t. So k is equal to omega n square means 1.142 whole square into t, 1.094. So we will find out the value of k here. 1.142 square into 1.094. It is 1.426. So we have found out the value of k and t. So let me verify here. K is 1.42. We have got it. And the value of t is 1.09. Okay, it is fine. It's correct. If any doubts are there at any moment, please don't hesitate to ask the doubts. Please you clarify the doubts as and when it comes to you. Please unmute yourself and speak to me so that I can clarify your doubts, right? Okay. I will proceed with the next numerical. For the RLC series circuit shown in the figure, determine the undamped natural frequency. Undamped natural frequency means omega n we have to find out, and damping ratio of the circuit means z we have to find out, right? Determine the undamped natural frequency omega n and damping ratio of the circuit z. Assume zero initial conditions. Yes, this is a given RLC circuit. The value of resistance, inductance and capacitance is given, right? Okay, what we will do, just we will convert this to Laplace domain, Laplace electrical network, Laplace domain, right? So the electrical network in Laplace domain, we'll convert this to Laplace domain. So just R as it is, then L is replaced by SL. You know it, right? Already we know this. It is SL in Laplace domain, right? SL, and here it is 1 by SC. 1 by SC. C is replaced by 1 by SC. You know it, right? Okay, this is V naught. So here I will call it as V naught of S. V naught of S. And input here it's Vi of S. Here. Vi of S. And it is 6 volts, right? And current I is flowing. Let me take here current I of t. Here in Laplace domain it is I of S. So we'll get that this is the Laplace domain electrical network. Laplace electrical network, right? So this is the in Laplace domain. So what we'll do, we will take the transfer function. The transfer function is the ratio of V naught of S by Vi of S, right? So V naught of S by Vi of S. So what is V naught of S? The voltage across the capacitor. So into I of S. But I of S in both numerator and denominator it will cancel. So I will write only 1 by SC. V naught of S is 1 by SC divided by, right, the voltage across the capacitor, 1 by SC into I of S. But I of S in the numerator and I of S in the denominator, they will cancel. Then Vi of S is equal to, what is Vi of S? R plus SL plus 1 by SC, right? Into I of S. I of S will get cancelled. So R plus SL plus 1 by SC. So into I of S, it will get cancelled, right? So if I write I of S here and here, they will get cancelled. I of S here and I of S, they will get, I'm not writing, right? So the next, we have to convert it into a standard form. So here, let me take L common, something we'll see. So 1 by SC is there, SC. So let me take SC as LCM in denominator and numerator. So SC will cancel in the numerator. So 1 by, so SC I am taking, so it is cancelling. So SCR, take LCM, right? So SC, S square LC, S square LC plus 1. So take LCM, right? SC will get cancelled. So SCR plus S square LC plus 1. So let me rewrite this. 1 by S square LC plus SCR plus 1 S square, right? Okay, but I want this is the standard second order, but LC should be removed, sir. So let me rewrite it once again. V naught of S by Vi of S is equal to 1 by, observe here, I will take LC outside here. So LC means I'll take it to numerator. 1 by LC, it will become 1 by LC. So LC is taken out. So S square plus, so LC is taken out, right? So LC is taken out means C is there. S into R by L will become S into R by L. So LC is taken out, right? You multiply LC, LL will get cancelled, SCR I am getting back. Is it fine? So here LC is taken out, 1 by LC it will become. Just multiply LC for it, it will become, will get 1. So it is correct. So call this as equation 1 and compare with the standard second order equation, right? So S square plus 2Z omega ns plus omega n square equal to 0. This is the standard second order system, right? Standard form of second order system, SOS. So compare this equation with this, right? So omega n, so S square plus 2 omega n square, right? Omega n square is 1 by LC. Omega n square is 1 by LC. Just compare. Then 2Z omega n is R by L. 2Z omega n is R by L. Omega n is R by L. So in this, it is asked to find out the undamped omega n and Z, right? So they have given the values. So we will make use of those values. Omega n square is equal to 1 by L into C. What is L? L is 10 millihenry. 10 milli means 10 power minus 3. And capacitance 0.01 microfarad. 0.01 micro means 10 power minus 6. We will calculate this. So omega n square equal to, so what I will be getting, let me check it. So 10 exponential 10 into 10 to the power of minus 3, 10 to the power of minus 3 into 0.01 into 10 to the power of minus 6. So I'll take inverse. I am getting 1 into 10 1 into 10 to the power of 10. So I want omega n, take root of that. So I'll be writing the final value. Omega n equal to take root of this, root of the answer. So I am getting answer as, let me write it as, let me express in a 0.1 into 10 to the power of 6. 0.1 into 10 to the power of 6 radians per second. Or else you can write, okay, fine, this is fine. Okay. Then we'll find out, we came to know omega n, we'll find out Z, right? So Z is equal to R by L into 1 by 2 omega n. So we'll find out this. So what is R? R is 1K. 1K means 1 into 10 to the power of 3. 1 into 10 to the power of 3. L is how much? 10 millihenry. 10 to the power of minus 3 into 1 by 2 into omega n is 0.1 into 10 to the power of 6. Right? So we'll calculate this. Okay, fine. Observe here. Let me simplify it. 10 power 3 is there, right? So what will happen? 6, 10 power 6 is there. 6 minus 3. 6 minus 3 is 3. 3 plus 1, 4. Right? 10 power 4 is there. Let me take this 10 power 3 below. Right? So for 10 power 4 minus 4 minus 3, 10. Only 10 it will become. So let me rewrite it. So 6 minus 3, 3. 3 plus 1, 4. 4 minus 3, 1. So I am getting totally 10. Right? So 10 into this, everything we have taken care already. Right? 2 into 0.1. So we'll calculate this. So 10 into 2 into 0.1. So I'll take inverse of this. So 0.5, z equal to 0.5. So let me verify the answers here. So this problem is 4.11. So the value of z is 0.5, it is correct. And the value of omega n is 10 power 5 radians per second. 10 power 5. I can write this as 10 power 5 radians per second, no? Right? No problem. 10 power 5 radians per second. One and the same. 0.1 into 10 power 6 are 10 power 5 radians per second. One and the same. Right? Okay, we have for the given RLC circuit, we have found the damping undamped natural frequency omega n and the damping ratio or damping factor z. Is it fine? Okay. Any doubts? Please unmute yourself and talk to me. Okay, shall I proceed with the next? Okay, let me take this numerical. A closed loop control system is represented by the differential equation d square c by dt square plus 4 into dc by dt plus 16e. So c of t is the response. C means c of t. E means e of t. E of t is error signal, C of t is response of the system, right? Where E is equal to R minus C means E of t, the error signal E of t is equal to R of t, the input, reference input minus C of t, right? They are functions of time only. Simply we can write T equal to R minus C. It is the error signal. Determine the undamped natural frequency means omega n we have to find out. The damping ratio Z we have to find out. And the percentage maximum overshoot for unit step input means percentage MP we have to find out. So all these things we have to find out. Okay, we'll proceed. Okay, let me write it. D square C by dt square plus 4 into dc by dt. What is E? Instead of for E, I'll substitute R minus C, right? 16R, R minus C. Let me multiply and write it. 16R minus 16C. I have substituted E equal to R minus C and multiplied by 60. 16R minus 16C. Is it fine? So take C terms, response one side, right? So d square C by dt square plus 4 into dc by dt. This plus 16C plus 16C is equal to 16R. So these all are functions of time, R of t, C of t, right? Take Laplace transform of the above equation. Take Laplace transform of above equation. So what I will be getting? S square into, yeah, right? C of S. S square into C of S. So C of S, C of S, C of S. Let me take it common. C of S is outside. So if from this I am getting S square, C of S is taken outside. The next from plus 4S into C of S is already taken outside, plus 16 into C of S is already taken here. Then 16 into, it is R of t means R of S. Next I will get the transfer function. Let me write it here. I will continue here. Okay. Then next C of S by R of S. C of S by R of S is equal to 16 divided by S square plus 4S plus 16. Call this as equation 1. Then compare this denominator polynomial with the standard second order equation. S square plus 2z omega ns plus omega n square equal to 0. Compare. So after comparing, so I'll be getting omega n square equal to 16 and 2z omega n is equal to 4. So omega n root 16 is 4, right? So find out the value of z. Z is equal to 4 by 2 times omega n. So 4 by 2 times omega n is how much? 4. So 4 will get cancelled. 1 by 2 is 0.5. So z equal to 0.5. Right? Let me verify the answer here. 4.13. The value of z turns out to be as 0.5, it is correct, and value of omega n is 4, it's correct, right? Okay, but here still it's not over. We have to find out the undamped. Okay, we have found out w omega n and z. This is over, omega n is over, then z is over. Then we have to find out percentage peak overshoot mp. Okay, we'll proceed. So first, before finding out the percentage, just simply we'll find out peak overshoot mp. So we know the formula, e to the power of minus pi into z divided by root of 1 minus z square. You have to remember the formula, there is no other alternative, right? So e to the power of minus pi into z is how much? It is 0.5. 0.5 divided by root of 1 minus 0.5 square. So we'll find out how much we'll get. So e to the power of minus, we'll simplify this. So root of 1 minus 0.5 square. So denominator I am doing first. Take inverse of it, it will go to numerator, into pi into 0.5. So I will be getting overall 1.8137. 1.81. We will do this. Shift e to the power of minus 1.8137. So I am getting it as 0.1630. So I want percentage peak overshoot, just multiply by 100. So multiply by 100, I am getting 16.3%. Right, this is the percentage peak overshoot, right? And it is correct. Okay. So this variety of problems are there. So we'll stop the problems here and we'll continue with the next topic, right? Steady state errors and error constants. Yes, steady state errors and error constants. Okay. And we already know the response of first order system and second order system for unit step input. Let me draw it here. For first order system, this is the response we got. Just observe here. This is the time axis and this is the response c of t. And the reference unit step input. This is the unit step input, right? This is one unit step input, right? This is the unit step input. So for first order system, we got rising exponential, right? So it rises and it reaches the steady state value or final value at time t equal to infinity. Suppose instead of rising like this, okay, let me change the color of the ink. Suppose it rises slowly. Then suppose if it does not achieve the steady state or final state, if there is any difference between the desired output and the actual output, this is the desired and actual output, then there exists steady state error ESS, right? But for first order system and second order system subjected to unit step input, we have found out that the steady state error is 0. Already we have seen this, right? Means the output follows the input. The output tracks the input at time t equal to infinity, right? Okay, when the steady state error occurs, whenever there is a difference between the desired output and the actual output, like this, right? Okay, this is for first order system. Similarly for the second order system, so this is time t, this is the response c of t, and the unit step response, this is the unit step response. And for second order system, we got damped oscillations, right? So damped oscillations, and suppose at time t equal to infinity, suppose this is the response, if it is not achieving, then there is a difference between the actual output and the desired output. This was steady state error. But for second order system, the steady state error is 0 means, so it will track, the output will track the input, right? So these things we should be knowing, what is steady state error. And these error constants, we'll study about this error constant. There are 3 types of error constants: position constant, velocity, acceleration, right? We'll see that velocity, acceleration, velocity constant and acceleration constant. Error, these are the error constants. What is this? We'll see it one by one. And why we should study this steady state errors? By looking at the steady state errors, we will come to know that whether the system will reach the final value or steady state value or not. If the system reaches the final value or steady state value, then the such systems will be considered stable systems. If the output, or if the system does not reach the steady state value or final value, and if there exists a steady state error, then we say that such system is not stable system, right? Okay, fine. So okay, fine. Steady state errors, they constitute an extremely important aspect of system performance, right? We will make use of this steady state error in order to get the system performance, right? That we'll see. And in order to find out the system accuracy, this steady state error is nothing but the measure of system accuracy, right? Because whether is there any difference between actual output and desired output, that will come to know, right? If the steady state error is 0, the system is 100% accurate. If there exists the difference between actual output and desired output, means if there exists the steady state error, the system is less accurate or not accurate, right? We'll see that. Then these steady state errors, they arise from maybe based on the inputs what we are applying to the system, or the type of the system, whether it is type 0 system, type 1 system, type 3. We know this. What is this type 1, type 0, right? Type 0, type 1, and so on, type 2, and so on. And also the non-linearities of the system components, right? There are several components making the system. If the components are non-linear, then also there exists the steady state errors, right? Maybe based on because of the inputs or the type of the system and the non-linearities of the system components, the steady state error occurs in the system. Okay, we will try to understand. Okay, we'll try to understand the steady state error. We will take the unity feedback system. You can observe here. 1 minute. Let's fine. Okay, I'll change the ink color. Okay, this is the unity feedback system. R of s is the input, G of s is the forward path transfer function, C of s is the output, and H of s, the feedback path H of s is 1, and B of s is feedback signal, E of s is error signal. Then the closed loop transfer function of the given unity feedback system is given by C of s by R of s is equal to G divided by 1 plus G H. H is 1, H of s here, right? H of s, it is equal to 1. So G divided by 1 plus G H, H is 1. So we are not writing. Then what about, okay, this is fine. This is the transfer function. The error signal. How to write this error signal? I'll tell you. See here. What is C of s? C of s is equal to E of s into G of s. So let me write it here one more step. What is C of s? C of s is equal to E of s into G of s, right? E of s into G of s. But I want the error signal. So error signal E of s is equal to C of s divided by G of s. So the same thing they have written here. E of s is equal to C of s by G of s. Is it fine? Okay. Then we will substitute what is the C of s and G of s. Is it fine? So let me write it here. Let me take E of s is equal to, what is C of s? C of s is this one. So take this R of s this side. So C of s is, take this R of s this side, R of s into G of s divided by 1 plus G of s. This is my C of s, right? Because C of s by R of G of s. C of s is, take this R of s this side, right? R of s into G of s 1 plus G of s divided by G of s. Yes. So G of s will get cancelled. So what I am getting, E of s is equal to R of s divided by 1 plus G of s. The same thing has been written in the next slide, right? So the error signal E of s is equal to R of s by 1 plus G of s. Yes. Okay. You can observe here the error depends on the, we have told already, the error depends on the input of the system, right? Also it depends on the forward path transfer function G of s. Okay. Let me rewrite this equation once again. E of s, R of s is taken this side. So E of s by R of s is equal to 1 by 1 plus G of s. Okay. We'll see whether this equation is used or not further. Then we know the steady state error is may be found by using the final value theorem. What is this final value theorem? I will tell you, right? Okay. What is steady state error? ESS, right? It is equal to limit t tending to infinity E of t, right? Okay. When the steady state error is obtained at time t equal to infinity, right? And we look at any errors in the time domain. So limit t tending to infinity E of t is nothing but ESS. This we know. And we will make use of the final value theorem in order to find out the steady state error ESS. Yes, if anything is like this, limit t tending to infinity, if it is function of f of t, for example, here f of t is nothing but error signal E of t, then by making use of final value theorem, you already know the final value theorem in Laplace domain. From time domain, it will be converted to Laplace domain, s tending towards 0. Here t is tending towards infinite means s tends towards 0 into f of s. S into f of s, sorry, s into f of s. So this is the final value theorem, right? So we will apply this final value theorem. So limit t tending to infinity e of t. Limit s tending to 0, s into e of s. Is it fine? S into f of s. Here s into e of s. Is it fine? Okay. Then what is e of s? We'll substitute. E of s is r of s divided by 1 plus. We'll substitute here s into r of s divided by 1 plus g of s. So this is the steady state error. We can observe the steady state error depends on the type of the input r of s and the forward part transfer function g of s. Is it fine? Okay. Right now we will not substitute s equal to 0. Right? We will make use of this steady state error, general equation of steady state error. For other types of type 0 system, type 1 we'll see next. Right? And this equation 4.20, in order to maintain uniformity with the textbook, I have written the equation numbers. And this equation 4.20 for ESS shows the steady state error. It depends on, already I told, it depends on the input R of S and it depends on the forward part transfer function G of S. Already I told this. Is it fine? Okay. I hope you came to know the steady state error depends on the input of the system and the forward part transfer function G of S. You should remember this, right? Okay. Then next we'll proceed with the steady state errors and error few in detail, right? So steady state error we came to know. Steady state error depends on the input of the system, type of the input of the system, and forward part transfer function. Then what are these error constants? We'll try to understand what are these error constants now, right? Okay, there are three types of error constant: static position, static velocity, static acceleration. Kp, Kv, Ka. Kp, Kv, Ka. Right? We'll see one by one. If the input of the system is unit step, then we call it as position. If it is unit step, this is input of the system. If the input is unit ramp, then we call it as velocity constant. If the input is unit parabolic, then we call it as acceleration constant. So we'll study all these types of error constants with respect to unit step input, unit ramp input, and unit parabolic input, right? So the input for the system here, R of S, can be unit step or unit ramp or unit parabolic, right? So if it is unit step, there exists some error in the system. That error we call it as position constant, position error constant, right? Or position, right? Then if the input is unit ramp, then we call it as velocity error constant, Kv. If the input is unit parabolic, we call it as acceleration constant, acceleration error constant, Ka. Kp, Kv, Ka, based on the type of the input we apply for the system, right? Okay, we will study first the static position error constant, Kp, right? So static position error constant. Okay. P stands for position, right? Position error. K is for constant. So position error constant, Kp, right? Position error constant. Got it? Right? Static means we are taking the initial, we are assuming the system to be at rest, assuming initial conditions to be 0. Hence we call it a static position error constant, right? Kp. Okay, the steady state error. What is ESS? We have to study for this kind of. So the steady state error of the system for unit step input R of t is 1. So Laplace domain R of s is 1 by s. If the input for the system is unit step input, right? Unit step input, then R of t is 1. Then Laplace domain R of s is 1 by s. Then at that time, what is steady state error? We know the steady state error just now I shown you, right? The steady state error in time domain, limit t tends to infinity e of t. But in Laplace domain, using the final value theorem, I can write it as limit s tending towards 0, s into e of s. We will make use of this. Is it fine? So the same thing has been made use here. ESS limit s tending towards 0, s into e of s. What is this e of s? Already we have seen for this system. What is e of s? E of s is r of s by 1 plus g of s. So we'll substitute here r of s divided by 1 plus g of s. Okay, fine. What is R of S? R of S is 1 by S. So substitute. So S into, what is this R of S? It is 1 by S. So the remaining denominator as written. So SS will get cancelled here. S will get cancelled. So what I will be getting? So apply the limit S tending towards 0, right? So 1 divided by 1 plus. So I cannot apply the limit for the constant. So apply the limit for this function. So 1 divided by 1 plus limit S tending towards Z of S. Is it fine? This limit has been, I cannot apply the limit to the numerator. It is constant 1. I cannot apply the limit to this constant, so I will apply the limit here only to this term in the denominator. So 1 divided by 1 plus limit s tending towards 0 z of s, right? Just substitute s equal to 0. So 1 divided by 1 plus g of 0. And this g of 0 I will call it as position error constant kp. 1 divided by 1 plus kp. Okay. This is the steady state error whenever the system is subjected to unit step input. So we got the steady state error as 1 divided by 1 plus kp whenever the system is subjected to the unit step input. Please keep in the mind. So the steady state error, what we got? 1 divided by 1 plus kp. Kp is position error constant. And what is kp? How we got? So this, just observe here. Kp is nothing but this one. Limit s tending to z of s. So this is limit kp is equal to limit s tending z of s. That is nothing but g of 0. And this we call it as position error constant. So you should understand two things. Whenever the system is subjected to unit step input, the steady state error, what we are going to get? 1 divided by 1 plus kp. And what is this kp? How to find out this position error constant? Limit s tending towards 0 z of s. It is nothing but z of 0. This, right? So we have seen the steady state error and the position error constant. Okay, whenever the system is subjected to unit ramp, similarly we will do the same analysis whenever the system is subjected to unit ramp instead of unit step, right? We'll see next. So static velocity error constant, velocity error kv, velocity error constant kv, right? Is it fine? So when we use this velocity error constant, whenever the system is subjected to unit ramp input, observe here, unit ramp input. So the steady state error for the system subjected to unit ramp input. Unit ramp input is r of t is nothing but t. And what is r of s in time domain? So it is 1 by s square. Whenever the system is having unit ramp input, so the input r of s in Laplace domain is 1 by s square. We know this, right? So we'll make use of how we'll find out the steady state error by making use of the final value theorem. ESS is equal to limit s tending to s into e of s. This we know, right? So s tending to s into what is e of s? R of s divided by 1 plus g of s. Then what is r of s? It is 1 by s square. Substitute here. So s will get cancelled. So I will be getting ss. So 1 by s I will be getting. So let me rewrite it here once again. Right? So limit s tending towards 0. So ss will get cancelled. 1 by s I will get. So what I will do? 1 by I will multiply with this s in the denominator. S into 1 is s plus s into g of s. Then I will apply the limit. So limit s tending towards 0, 1 divided by, if I substitute s equal to 0, this will vanish. So here, if I substitute, I have to apply the limit s because I don't know g of s here. So I will not apply s equal to 0 here right now. So limit, I will apply the limit. I cannot apply the limit for the numerator as it is constant. If I apply the limit s tending towards 0 means, yes, if I substitute s equal to 0, this term will vanish, right? This term will vanish if I apply the limit. So what I am left out, limit s tending towards 0, s into g of s. The same thing has been written, 1 divided by limit s tending towards 0, s into g of s. So this entire thing will replace it by the velocity error constant, 1 by kv. Means I came to know that the steady state error is 1 by kv whenever the system is subjected to unit ramp input. And what is this? How to find out kv? Velocity error constant. So it is limit s tending towards s into g of s. This we call it as velocity error constant. So observe this and previous one. The steady state error whenever the system is subject to unit step input is 1 divided by 1 plus kp. Here it is 1 by kv whenever the system is subjected to unit ramp input. And kp is limit s tending to g of s. Here kv is limit s into g of s. Right? You remember this. You have to remember these things. Then next, whenever the system is subjected to unit parabolic input. Right? So at that time the error that exists in the system we call it as acceleration error constant, Ka, acceleration error constant Ka, right? So whenever the system is subjected to unit parabolic input, so r of t is t square by 2, right? We know this. Then take the Laplace transform of it, r of s is equal to 1 by s cube, right? So whenever the system is the input is unit parabolic, so its input is r of s in Laplace domain, it is 1 by s cube. So we will make use of the steady state error, the same thing what we have done earlier two cases. The steady state error ESS is equal to s tending towards 0, s into e of s. This we know, right? This we know. So limit s as it is. E of s is r of s divided by 1 plus g of s. What is r of s? Here it is 1 by s cube. Substitute here. So what I will be getting, just I will write it here. Limit s tending towards 0. So s will get 1 by s square. I will multiply here s square 1 by s square into 1. So s square plus s square into g of s. So I will apply the limit here. This term will vanish after applying the limit, this first term. Then we'll apply the limit for this. So yeah, so first term vanishes, 1 divided by limit of this. So 1 divided by limit of s tending to s square into g of s. So this entire term I will call it as error constant. So the steady state error whenever the system is subjected to unit parabolic input is given by 1 by Ka, acceleration error constant. And what is this acceleration constant? It is limit s tending to s square into g of s is defined as acceleration error constant. So you have to remember all these things, right? So let me recall what I have done. What is the steady state error whenever the system is subjected to unit step input? 1 divided by 1 plus Kp. This is for unit step. Then whenever the system is subjected to unit ramp, what is ESS? I am going to get 1 by Kv, velocity error constant. Whenever the system is subjected to unit parabolic input, then the steady state error ESS is 1 by Ka. Then what is this Kp, Kv, Ka? Just I will list out here. Observe here. Kp, Kv, Ka. Limit s tending towards 0. Limit, this is fine. This is common for all. Limit s tending towards 0. Here it is g of s. Right? For Kv it is s into g of s. For acceleration constant it is s square into g of s. Right? I hope you understood. This is for unit step input. The error whenever this is the position error constant whenever we apply the input for the system as unit step. Whenever we apply the unit ramp input, the error, that is velocity error constant, limit s tending to s into g of s. Whenever we apply unit parabolic, the acceleration constant k is equal to limit s tending to s square into g of s. Right? All these things we have to remember. Just I have summarized for your convenience. Okay, I will not go to this. I'll stop here only because the topic is very tedious. So, if any doubts are there, you can ask me. I'll stop recording.